Hello class. Polar coordinates, which offers an alternate way to describe a location on the xy plane. Alright, so the first thing I want to point out is I have adopted the convention of putting two numbers separated by a comma and putting them in brackets to indicate that we're talking about polar coordinates. The first coordinate is typically referred to as the r and the second one is the theta. The second number is the one I typically focus on first. Theta is an angle, and it'll be obvious because you'll see a degree sign, but sometimes it's not obvious because your unit might be in radians. All right, so the first thing is focus on the angle, 30 degrees. Go to your circle here, and this 30 degrees should be interpreted in standard position. Therefore, we're starting with the positive x-axis and going from there. Positive angles are going to be counterclockwise and negative angles are clockwise. So we go to an angle trajectory indicated by the 30 degrees, and 30 degrees is here at pi sixth. And then this first number is the r. This says how far the point should be from the origin. In this context, we tend to call the origin a different word. We use the pole, P-O-L-E. And then you simply go out a distance from the pole, and you go out a total distance of 2 units. And you see these concentric circles. That's to help us figure out how far certain distances are from the origin. And then that takes us to this location right here. And so this is the location of point A. Okay, let's look at point B. All right, here's a negative angle here, so we go clockwise 45 degrees, and then we go out 2.5 units away from the origin. There's our negative 45 degree trajectory, and then we go 2.5 units away. Each little ring here is a half a unit. That's 1 unit. There's 2 units, and there's the extra half. Point B, along a trajectory of negative 45 degrees and 2.5 units away from the origin. All right, the next one, point C. How to interpret when there's a negative r. When you have a negative r, you still focus on this angle here. So we're going to do a positive 300 degrees. Well, 300 degrees is 60 degrees less than doing a full rotation. So really I could go clockwise 60 degrees, and that would get me to the same trajectory as going counterclockwise 300 degrees. Here's our 300 degree trajectory along this line here. So now we have a negative radius. If that was a positive one, then I would go right here and say there's my point. But when you have a negative radius, you actually want to extend the trajectory the opposite direction of the pole. So negative radii, you go the opposite direction of that angle. Extend that trajectory back through into the second quadrant, and keep in mind that 300 degrees is still focusing on this direction. But when you have a negative r, you go the opposite direction. So we're actually going to wind up putting a point right here. So there is our point C. Point D, 7 pi sixths, and then go out 3. That takes us to this location, 7 pi sixths, and then go out a total distance of 3. So that just puts us right there. That's point D. Point E, go negative 3 pi halves, but then do a negative 4 radius. Focus first on this negative angle. So here's negative pi halves, negative pi, and negative 3 pi halves. So negative 3 pi halves is actually pointing up this way. But instead of going out 4 units, right, all the way out to here, we go the opposite direction. So we're actually going to go down with this point, not up, even though the angle is having us look up. And we go the opposite direction this way, 4 units, until we get to a point, it's point E. Point F, so 7 pi, let's see where that winds up. Here's pi, here's 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. So 7 pi is just a lot of rotations and eventually winds up pointing in the same direction as just pi. Okay, so we have 7 pi is pointing out this direction, and then we look at this 1.5 and just go 1.5 units out in that direction. So that takes us to right there, and that is point F. And now let's focus on point G. So G says go to an angle of negative 2 pi, so that's clockwise 2 pi. We're still pointing this direction. But then when you have an r of 0, that just means don't go anywhere. You just put a point right here at the origin, and this would be point G. Now you might realize at this point here that you could describe that point no matter what angle I put here. If the radius is 0, that means don't go anywhere from the origin. So it really doesn't matter what angle you're pointing at. If you go 0 units away from the origin, you're going to stay at the origin. Which actually introduces the realization that there's going to be lots of different ways to describe these points using polar coordinates, right? Because this location is the same as this location. In fact, all of these points that we're describing could be described in multiple ways. Let's go ahead and finish and do H. All right, so you have to be careful here. We still interpret the first coordinate as r and the second coordinate as theta. So just because you see a pi here, don't think that that means that should be the theta and that should be the r. So we're going to go about 3.14 units along a trajectory of 1 radian. So we have to remember what 1 radian is. When we do a conversion of radians back into degrees, 1 radian was a little bit less than 60 degrees. Somewhere along this trajectory is 1 radian. and then we go a distance of pi in that direction. 3.14 is somewhere a little bit after 3, and this would be point h. All right, some people will see this, and because our brains are now trained to see a pi and think that that means an angle, if you went pi radian in 1 unit, that would take us to this location, right? Not at all the same interpretation as going 1 radian and then going out pi units. So just be careful when in polar coordinates, the first number should be interpreted as a distance and the second number should be interpreted as an angle. And if you don't see a unit, interpret it in radians. Okay, now just to illustrate some of the complexity of labeling these points in polar coordinates, let's just focus on point B. Point B was originally presented as the point of saying, go out 2.5 units along a trajectory of negative 45 degrees. But you can get there by multiple ways. Instead of going negative 45 degrees, you could go positive 315 degrees and go the same 2.5 out. Right, here's a different way to wind up in the same location. Or you can rotate 135 degrees, which would rotate us to right here, but then instead of going out 2.5, go out negative 2.5. So you could also say that point B is found by go negative 2.5 distance while pointing in the direction of 135 degrees. And we could actually keep going. I could do counterclockwise rotations, I could do clockwise rotations, I could do positive or negative R's to get to my location, and I could rotate around the circle a whole bunch of times before I settle on a trajectory and then do my R. So there's really infinitely many ways you could describe the same location when you're using polar coordinates. That's not true with rectangular coordinates. All right, let's take a look at the next slide. We're going to come up with a relationship between polar and rectangular coordinates that allow us to make conversions back and forth. Let's put our point right there. It's a certain distance away from the origin. The x coordinates and y coordinates are used to go horizontal and vertical to get there. So that's using rectangular coordinates. The polar instructions would say go a certain theta, but then go a certain r out to get there. We're going to put our point here in the first quadrant in this diagram and just come up with a relationship between x and y and r and theta. Like if I know x and y, how can I convert that to r and theta? If I know r and theta, how can I convert that back into x and y? Well, some obvious relationships that we see here. If I know x and y, I can always find r. I can just do the Pythagorean theorem. So I know that this statement is going to be true. And I also know that if I know x and y and I'm trying to find theta, I know that the tangent of theta will involve opposite over adjacent. So whatever theta is, I know that the tangent of theta will be equal to y divided by x. You have to be careful about this statement right here, because if I'm solving for theta, I'd do an arctangent next. But arctangent has a range that only spans from negative 90 degrees and then rotates this way to positive 90 degrees. So when you're solving for theta and you're going to use an arctangent, you're going to have to maybe adjust your answers to make sure that you're at an angle in the correct quadrant. Regardless, if I know x and y, these will be useful relationships to help me find what r and theta are. What about the other way around? Suppose I know this information and this information, how would I find these sides? To go the other way around, so I know that the sine of that angle is equal to the opposite, which is y, divided by the hypotenuse, which is r. And then multiply r to the other side, you get y is equal to r sine theta. So if you know r and you know theta, then you can do this calculation right here and you would get the y coordinate in rectangular. Now we want a way to find x if I know r. So I want to use these two sides and the same angle theta. And so the x is the adjacent and the r is the hypotenuse. And so cosine of theta is equal to x, which is the adjacent, divided by r, which is the hypotenuse. And then solve this for x. So we get x is equal to r cosine theta. All right, so these formulas up here we'll use when we want to go from x and y and convert to r and theta. These here we'll use when you know r and theta and you're trying to convert to x and y. Okay, let's do some examples of this. Converting between Cartesian and polar coordinates. So here we have a point given in polar coordinates and we're asked to figure out what its Cartesian, which is the rectangular coordinates, will be. We're given r and theta, and we're asked to find what x and y would be. So let's first plot the point and see roughly where it's at, so we know what quadrant to expect our x and y to be. So this was a 30-degree mark. So remember, each of these rays that you see here in our diagram represents 15 degrees. So the 15-degree ray is right here. So that's our 15-degree trajectory, and then we do a negative 3r. If it was positive, be right here, but negative 3 comma 15 degrees is over here. So that's our location. We want to find the rectangular coordinates for this. Well, clearly it's going to involve doing some sort of negative x followed by doing some sort of negative y to get into the third quadrant. Okay, to find the x coordinate, x is equal to r cosine of theta. Okay, so in this case, the radius is negative 3 and the angle is 15 degrees. Let's go ahead and just use Desmos here to approximate this. Notice it's giving me a positive result. That's because Desmos, when you open it, it defaults to radians. You got to make sure you're in degrees. Build a habit of clicking this wrench right away and making sure you're in the right unit as far as angles are concerned, so degrees. Okay, now we get this negative 2.898, we'll say. Right, that would be this negative distance that we go here. So the y-coordinate is equal to r sine theta. R is negative 3 and theta is 15 degrees. And there we go, negative 0.776. And that's how far down we would drop to get to that location. So our final answer, we're going to go about 2.898 left, followed by going about 0.776 down, taking us into that third quadrant to describe that location using rectangular coordinates. All right, going this direction is always very easy. And by this direction, I mean going from a polar coordinate to a rectangular coordinate. Right, the trouble is going to come in the other direction. Convert between Cartesian and polar coordinates. Convert the given point in rectangular coordinates to polar coordinates. Give two answers where theta is between 0 and 2 pi, and then two more answers. So there's going to be lots of different ways we can answer this question in general when you go from rectangular to polar. So let's begin by identifying the location. Notice it's in parentheses, so that's a good indication. You should interpret these numbers as rectangular coordinates. So go left 3, then up 2. That takes us to this location right here. Now our goal is to figure out how far this point is from the origin. That's going to be the r. And we want to figure out what angle trajectory to use. So our goals are to find this theta and this r. Okay, we're going to find different ways to use these formulas. So you could, draw your right triangle here, and you could ignore the fact that these are negative or positive. I mean, this is just 3 units long, and that's 2 units long. Use the Pythagorean theorem, and you can figure out what r is. So we have 3 squared plus 2 squared. Or if you insist, you can put, the negative on that 3. But since you're about to square, it doesn't matter. It's going to be treated as if it was positive 3 in the first place. And this is equal to r squared. And that gives us 9 plus 4 is 13. And then that's equal to r squared. So r is equal to the square root of 13. So it's about 3.6. Now let's find the theta next. So we're going to take this statement here and solve for theta by doing an arctangent. So whatever theta is, we know that the tangent of theta will be equal to y over x. So you just take the y-coordinate, which is 2, and divide it by the x-coordinate, which is negative 3. Therefore, theta will be equal to the arctangent of negative 2/3. Okay, notice it gives us an angle that's a negative angle. So we'll just say negative 33.7 degrees. Okay, that's clearly not the angle I was looking for. I'm looking for a theta that's positive and more than 90 degrees because I wanted to go counterclockwise and wind up in the second quadrant. Well, the answer the arctangent is giving me is a negative angle that's pointing into the fourth quadrant. It actually gives me the angle, whereas if you were to extend this through the origin like this, is this angle right here, negative 33.7 degrees. Arctangent will only ever give you angles that span pointing down here, so negative 90 degrees up to 0, and then up to positive 90 degrees. If you need an angle that's not one of those, then you're going to have to adjust the answer that you get using the arctangent. So it's not correct to say that the theta is equal to arctangent. This part right here needs to be erased. If you want, you can call this an alpha. And alpha is equal to arctangent of 2 over negative 3, which is negative 33.7 degrees. Okay, so the question is, how do I get theta? Well, start with alpha and rotate counterclockwise 180 degrees, and that will point in the direction we want it to point. So theta actually needs to take alpha and add 180 degrees to it. And that theta is approximately 146.3. And let's make sure we follow all of the instructions that are here. Once we have the point described in one set of polar coordinates, it's not that hard to come up with others. So one answer to our problem is use brackets. So that r was radical 13 and the theta was approximately 146 degrees. If you want to be exact, you would write out 180 plus arctan of... This is the best thing you could say if you want to keep your answer exact. But let's go ahead and just put an approximate answer in here. And so it's about 146.3 degrees. It says to give two answers where theta 0 to 2 pi. So we want to make sure we get the right trajectory. So obviously here's one trajectory answer. But then we all want to rotate enough so that we're pointing this way, but then do a negative r to make sure we actually wind up going over here. So a second angle I could use is take this angle right here and go another 180 degrees. And so a second answer would be negative radical 13, and add 180 to this, we're going to get 326.3 degrees. And these are the only two ways that you can describe this point, insisting that you use an angle between 0 and 360 degrees. But these instructions say to give two more answers. One answer is to use the alpha that was given. This answer we got here right? So that's outside the window from 0 to 360 because it's negative, so it's less than 0. And that points us into the fourth quadrant, but then go the opposite direction. So another answer will be to go the opposite direction, negative radical 13, but do this negative 33.7 degrees. And then the final expression will be go alpha, but then clockwise go another 180 degrees. All right, so take this and go another negative 180. So that's going to be negative 213.7 degrees, and then we only have to go out a positive radical 13. And there are our 4 answers. Lots of different ways to describe a location in polar coordinates.